So this video is intended to give students an idea of how to solve a particle motion problem and hopefully how to correctly format that for students writing the AP Calculus exam. So we have a problem here that talks about a particle moving along an x-axis and its position is given by the function x at t equals 1/3 t cubed minus a half t squared minus 2t minus 2. And we see that this particle is in motion on the time interval from 0 to 10 inclusive. We're asked for the average velocity, when the particle changes direction, whether the velocity is increasing or decreasing after 1 second, and when, if ever, the particle is speeding up. In a question like this, we can see by reading it pretty much immediately that we're going to need both the velocity and the acceleration. And so I might be tempted to do those things first and get them out of the way before we go on to solving the rest of the problem. So before we start, let's do that. We're going to calculate the velocity, and it's not sufficient to just write the velocity down. We have to say how we're getting that. So we have to say that this is the time rate of change, the derivative with respect to t, of the function that we're given for x, and that's going to be t squared minus t minus 2. And then we may as well go right ahead and get acceleration at the same time. And again, we have to say how we're calculating that. So that's going to be the derivative of the velocity function we just got, and that's going to be 2t minus 1. Now that I've established what the velocity and the acceleration is, I can go ahead and use those functions for the rest of the question without having to worry about justifying them. So part A is asking for the average velocity. So velocity average on the interval 0 to 6. And we know the formula is just the change in position, x at 6 minus x at 0, divided by the change in time, 6 minus 0. And that's going to come down to 40 minus negative 2 over 6, which is 42 over 6, which is 7. We're given units in the question, and so we're going to be expected to give units in our answers. So this is 7 meters per second, and that's part A. Part B asks us when, if ever, does the particle change direction. So in order to find out if the particle is changing direction, the first thing we need to do is find out when the particle is either stopped or when the velocity fails to exist. So we begin by setting up v equals 0 or v does not exist. In most cases, the velocity will exist everywhere, as is the case here. And so we can just go ahead and say that v exists for all values of t in the real number system. That's usually the case, but we have to consider it every time just to be sure. When is the velocity equal to 0? Well, the velocity is going to be equal to 0 when our velocity function, which was t squared minus t minus 2, is equal to 0. And so we can see that this is going to factor out quite nicely into t plus 1 and t minus 2, which gives me two critical values, t equals negative 1 or t equals 2. But remember that the function originally was only defined from 0 to 10. And so t equals negative 1 is not allowed. And so we can save ourselves a little bit of effort there by just claiming that this is extraneous because it's not in our domain, the domain of the position function. So now we want to see whether it's changing direction at t equals 2. T equals 2 is the only place where it could change direction, and we do that looking at a labeled sign chart. What we want is velocity over here, and we see if I put a number less than 2, for example, if I put a 1 into my velocity function, up here I'm going to get 1 minus 1 is 0 minus 2, so that's going to be a negative number. Okay, I know that I can't go past 0, and I know that on this side I can't go past 10. So here, if I put a number between 2 and 10, like maybe 5, I would get up here, 5 squared is 25 minus 5 is 20, minus 2, that's a positive number. So my function is going to the left before 2 and to the right after 2. And now all I have to do is justify my answer. I have to write this down. Remember, on the AP Calculus exam, we are not allowed to read labeled sign charts. So this labeled sign chart is very helpful in terms of figuring out what's going on, but it will not be allowed as a justification for your answer. So we have to effectively take what's in the labeled sign chart and write it down. And so we say, therefore, the particle changes direction. And what we want to see here are two things. We want to see how does the particle change direction. So we're going to say changes direction from left to right. And we want to see the justification of that. How do we know it changes direction from left to right? Because the velocity changes sign. And we have to say how it changes sign. It changes sign from negative to positive at our time t equals 2. Okay, and that's a fully justified answer for part B. Then we move on to part C, which asks, is the velocity increasing or decreasing at t equals 1 second? A common mistake is that people think that velocity increasing or decreasing is synonymous with slowing down and speeding up, and it isn't. The velocity is increasing. The way we find out whether a function's velocity is increasing is the same way we find out if anything is increasing, by looking at its derivative. For example, if I want to know if a random function f is increasing, I look at f prime. If f prime is positive, then f is increasing. If f prime is negative, then f is decreasing. So if I want to know if the velocity is increasing or decreasing at t equals 1, I need to look at v prime, at the velocity prime, which is, of course, acceleration. So I take my acceleration function, which is 2t minus 1, and it's very simple. I just plug in the value I'm interested in. A at 1 is going to be 2 times 1 minus 1, which is 1 meter per second squared. And that is the derivative of velocity. So if the derivative of velocity is positive, that implies that the velocity is speeding up. And so we can just say that. Therefore, v is increasing where? At t equals 1. Why? Because the derivative of velocity is positive. Okay? And now we've got part C solved. That just leaves us with part D, which is the most difficult part, which is to determine when, if ever, is this particle speeding up. Well, what we need to remember is that speeding up implies that velocity and acceleration have the same sign. So that's what we're looking for. At what values of t do velocity and acceleration have the same sign? We've already looked at when the velocity is 0. We already know that the velocity is 0 when t equals negative 1 second and t equals 2 seconds. And again, our domain is from 0 to 10, so the negative 1 is going to be extraneous. And so we've already sort of looked at the velocity. Now we need to look at when the acceleration is 0 and doesn't exist. And so that's exactly what we do. We set acceleration equals 0, and acceleration does not exist. Again, it's going to exist most of the time, and it's going to exist everywhere in this question, so we just say, same as before, a at t exists for all values of t in the real number system. That will usually be the case, but it doesn't have to be the case. And if the acceleration does not exist, that means that's a time when potentially the acceleration changes sign. So we do have to consider that, but most of the time it'll exist everywhere. And now we just go back to a at t equals 0. A at t, we remember, was 2t minus 1. We set that to 0, and that's very easy to solve. And we get t equals 1/2 a second. And now we can set up our labeled sign chart, And we want to set up a labeled sign chart that lets us kind of compare what the velocity is doing and what the acceleration is doing. So what we're going to want is a labeled sign chart with 3 vertical bars. One over here at time t equals 0, which we're not really too interested in. One at time equals a half. One at t equals 2, because that was where my velocity was 0. And then we go over as far as 10. It doesn't go past 10, but nothing's going to change anyway. On the left-hand side of this, we're looking at velocity and acceleration. And we remember that we can't look at anything over here because the particle's motion is restricted to positive numbers from 0 to 10. So now we just look at our signs for the velocity and acceleration. We remember that the velocity was negative to the left of 2. So that's a negative and that's a negative. And the velocity was positive to the right of 2. We already saw that. Now we look at acceleration, and acceleration might change sign at 1/2. So we look to the left of 1/2, say a quarter. And if I put a quarter into this, I get 2 times a quarter, which is a half, minus 1 is a negative number. So we've got negative there. Between 1/2 and 2, we put in maybe a 1. And if we put a 1 into this acceleration equation, we get 2 times 1 minus 1, which is a positive number. To the right of 2, we put in maybe a 5. 2 times 5 is 10 minus 1. That's another positive number. We were asked where it's speeding up. And remember, we know that speeding up means that velocity and acceleration have the same signs. And so those are my 2 intervals where it's speeding up. And again, I just have to remember that I'm not allowed to read the labeled sign chart. Okay, the labeled sign chart on the AP Calculus exam will not be considered as justification. And so I just take the information off of the labeled sign chart and write it in a sentence. So here I'm going to say, therefore, the particle is speeding up. And we have 2 intervals, but we have to justify them a little bit differently. So we start by saying, is speeding up on the interval 0 to 1/2. And a common question is, why is this square brackets, or should this be square brackets or round brackets? Should the interval be inclusive or exclusive? Different mathematicians have different opinions on this, but on the AP exam, we'll accept either. So from 0 to 1/2, and why is it speeding up there? Because velocity and acceleration are both negative. And then I can do the other one, and I can say it's also speeding up on the interval 2 to 10 because V and A are both positive. And that would be considered fully justified, and the question is solved. I would encourage you to pause the video at the beginning before you read this, or go back and try it again and answer the question on your own, and then check your work against mine to make sure that you've answered this correctly and that you've fully justified everything. As always, if you have any questions, let me know, and I hope this video has helped.